Okay, let's go. Last time we were talking about what is adequate sampling for an image, and basically you pick an amount of pollution relative error that you're willing to produce, and willing to bear, I guess I should say, and then you, if you know the RMS width of your camera's blurring function, then you can conclude that the pixel size needs to be a particular size or finer. Of course, finer means that you have to store more pixels than before, or more voxels in 3D. And so this is this was the conclusion that we came to last time. Any questions about that conclusion? Okay, so this is sort of people talk about that as preventing aliasing. What that really means is that frequencies that alias into the band from minus a half 1 over delta x to plus 1 over half delta x in the frequency domain have very, very little content, very low coefficients of the terms in that frequency, right? And so the question is, how do you make it if you have an image that is that is undersampled, that is to say, has a delta x that is larger than what you need? What can you do? And the short answer is nothing. Once you've badly sampled, there's not much you can do. Well, what you can do is to take your original image and blur it. Okay, so if you have a sampling interval that is such and so, according to your image. This guy is of width 1 over delta x. And you have image data that significantly is outside that. Well, you can try to damp out this stuff, right, by multiplying it by some further blurring function that is relatively high here. Let me give that another color. And that falls off like that, right? That's what you can. Okay, so you can essentially try to delete those higher frequencies that otherwise would pollute. Well, that indeed means that there won't be further aliasing of those frequencies. But on the other hand, you've lost the information about the original scene that is at those frequencies, right? So it's not a good choice. And so the deal is, if you're stuck with a particular image sampling rate, you've got to get rid of those frequencies before you put it into the computer. Okay, in other words, you've got to modify your image more or less non-computationally by some external means of making the frequency stick within the band that you're planning to sample at. Or alternatively, better, sample better in the first place. I note this exercise. and I take that seriously, and I want you to, for next class, I defined RMS width, and I want you to figure out what the RMS width is of a rect that is delta xy, right? We're talking about, and I'm talking in 1D. Okay, so this is that function, right? I will expect you to submit that calculation, and at the beginning of next class, I'm going to ask you all what you got. Submit it to Sakai. Okay, any questions about aliasing? I want to say a word about this multiplication I talked about. If you do it computationally, the aliasing has already occurred, right? In other words, this stuff is already in here. And if you blur that, it's going to get a blurred aliased image. Not a good thing. Well, if it's not too bad, if it's just like so, then you can say, well, my believable frequencies are here, and the pollution occurs basically from here to here, and then I can apply this. But it's really unsatisfactory. Make a long story short, don't incur aliasing in the first place. Sample satisfactorily. Okay. So we've been talking for a long, long time about using the eigenimages. I sometimes in the slides call them eigenfunctions. The eigenimages of shift invariant linear operators as basis images, and what is good about them? They are the Fourier images, the sinusoids. And the first is that they are the eigenimages of linear shift invariant operators. And the nice thing is that no matter what shift invariant linear operator you have the same eigenimages. The only thing varies operator by operator are the eigenvalue associated with those. They have a lot of nice computational properties. They're separable. You can apply them to rows and then columns of the result. You can, in 3D, you get, and then on that result you apply to the depth direction. They are rotationally invariant, meaning if you take a sinusoidal image and take an image and you rotate it, and then you do the sinusoidal decomposition of that, right? And then you rotate it back, you get the same as if you had done it with the original unrotated image. Okay, so that's pretty nice. You have this multiplicative decomposition property that I talked about last time that allows a divide and conquer algorithm, and thus a fast algorithm. And they're orthonormal. Well, they're orthonormal because they are indeed eigen images of something that is expressed in a matrix form, something that is, the matrix is symmetric, and symmetric matrices have orthonormal eigenimages. And as a result of all those things, fast calculation of the application of any of the whole family of shift invariant linear operators. Great. Computationally, that's really good in terms of efficiency. But we have talked about another property that is fairly nice about the sinusoidal representation, and that is if you have an image and you try to write it in terms of those basis images, the sinusoidal basis images, you will find that after a reasonably small number of basis eigenimages, if you organize them by level of detail, okay, which is essentially the wavelength, big wavelengths first and small wavelengths later, or alternatively low frequencies first and high frequencies later. The wavelength is just for a sinusoidal function, wavelength. We get darker pen, the black pen. Here it is. Wavelength. Is 1 over the frequency, right? And so if you organize them by low frequency to high or large wavelength to low, you will find that for real images, you won't need too many of those basis images. So you don't have to record a zillion sinusoidal coefficients in your representation. You can get away with way fewer, right? But if this is our objective, well, first of all, what does it buy you to be able to do that? If I know, instead of needing, if I have a 1,000 by 1,000 image, I would generally need 1,000,000 coefficients. What if I know that beyond the first 100 coefficients, all the rest is negligible? What's good about that? Yeah, we don't have to store the basic image anymore. We can just store the 100 coefficients, right? And so instead of having to have an image, I mean, we know computationally what the basis images are. We don't have to store them. We have formulas for them. If you want to store an image, well, all you need is 100 numbers, or, well, if they're complex, or as you know, there are really 2 sort of coefficients per frequency, so 200 numbers. But the point is that you need very few. You save storage. At least as important, where do we get our images from these days? Do I make my own images when I do my research? Where do we get them from? The internet, right? We get them from somewhere else. That stored them somewhere else and has to send them to us. If we can send 200 numbers, it's sure going to come faster than if we have to send 1,000,000 numbers. Right? So the coefficient list provides a compressed version of the image. A whole lot of compression. Okay? This, of course, depends on the image being relatively smooth, because that's what causes the only need relatively few coefficients, but that follows from the fact that images come from some kind of a camera. For those of you who are interested in medical images, as I am, the cameras we're talking about are CT imagers, MR imagers, ultrasound imagers, radiographic images, X-rays, etc., right? And those certainly have even worse resolution than pretty much all cell phone cameras, for example, from light images. Okay. By the way, for those interested, I've just seen an announcement of a new CT imager, CT so-called scanner, although it doesn't scan anymore, that improves the RMS width of the point spread function from around 1 millimeter, which has been the standard for years, to about 150 microns, a factor of sort of 6 better resolution. And so CT is going to change qualitative way in the kind of information it can show. But what does that mean? Okay, I said to talk to my colleague Mark Niethammer, Professor Niethammer. I said, we're going to be able to have images with 150 micron resolution. What do you think his response was? Oh my God, we're going to have to get way bigger GPUs, right? The number of pixels we're going to have to store is going to be much, much higher. Memory is a big deal when you're talking about these, especially 3D images that we're mostly dealing with when you're talking about these medical imaging devices. Okay. Before we leave the topic, what about situations where we have a linear operator, but it's not shift invariant? And basically the story there is you still have kernels, but at every position in the image, you have a different kernel. The kernel varies with position. In shift invariant operators, the kernel centered at some point in the image is the same kernel centered there, is the same kernel centered there. So you have a weighting function of the surrounding pixels that's given by the kernel. And that weighting function doesn't change except that it shifts its center to the pixel that you're trying to get your output at. Right? And what happens now is that you can, if it's still linear, you can still get a weighting function, but it changes as you move around the image. And then all of this technology of Eigen images that we've talked about doesn't work anymore. Okay, so what's wrong with it? Sounds wonderful. And if you go to the literature of image analysis, image processing, you'll see unbelievable numbers of papers and texts and so on. Oh, what wonderful thing sinusoidal decomposition is. Or they say thinking in the frequency domain. Well, the first thing that we might ask is, well, if what we're after is efficiency in storage or efficiency in transmission, that is to say, we call it image compression, can we do even better than the sinusoids? And the answer is we sure can. And that's the next topic of this course. How can we, if we want to give up the notion that it has to be good for shift invariant linear operators, how can we optimize compression? Require as few coefficients of the basis images as possible. What basis images will do that? Well, the answer to that question comes down to which kinds of images do you want to be good for? Right? If you're in the business of forestry, then you're going to be looking at images of trees from the ground, trees from above, forests in general, and you want to really be good have a really good basis set for that. If, on the other hand, you want to take pictures of, have portraits of individual people, then you want a basis set that's best matched to it. The point is, there's no general best set. You need a particular set of images that you want to use, and then we're going to collect a number, frequently a fairly large number of so-called training images, and we're going to try to figure out from that set of training images what's the best basis images that I should use for those training images. Okay? But here's the big, big problem with the Fourier representation. As it says here, it represents locality really, really badly. If I want to take a picture of Alan here in an image of the classroom, and he moves to the next chair, the difference between those two images is badly characterized by the changes in the coefficients in the frequency domain of the sinusoids. The reason is that position is characterized by phase, by the phase transfer, and not by the magnitude, mostly. So I'm going to give you a chance to do an exercise that's kind of fun. Take two images of two different things. I may have mentioned this before. You have magnitude phase after you do the Fourier decomposition, after you apply the DFT of one, magnitude phase of image B, A, and now take the image, the magnitude A, and put it together with the phase of B, and do your inverse Fourier transform. And take the transform of B and put it with the phase of A. And you get garbled images, you'll see. But the one it looks more like is the one it shares the phase with rather than the one it shares the magnitude with. Because our understanding from images is about the objects in the images, and the phase characterize where the objects are better. But the magnitude doesn't change if we translate the image around. But the phase does. But it does it in a very bad way, the phase. It sort of captures that, but it captures in a very garbled way because it has no locality. If only Alan moves and all the rest of you stay in your seats, you don't get a good characterization of the fact that he himself has moved. What I needed to do is to somehow get a little section of the image that's Alan alone, and if I could do that, then I could figure out that he'd move. But that begs the question, how do we handle this idea of analyzing images that have locality? And when I say locality, well, wait a second, what do I mean locality? Right? If I take a picture of Alan, he's going to look really big in my image. We want a sort of a relatively large region. If I take a picture of Emma back there in the back row, she is not much different in size in actual fact than Alan, but she looks way smaller in the image, right? Because of perspective. And so I need to be able to control the spatial scale of the locality that I'm talking about. I want to add a particular place in a particular region of a particular scale. And that's going to be the topic after we cover this first question of what's a best set for compression. And then we're going to go on to locality and scale. But to make a long story short, the basis that we've been studying, the sinusoidal basis, doesn't allow us to capture locality because each coefficient, whether it be the magnitude or the scale in the frequency domain, comes from the whole image and not just from a section of the image. Right? There's no locality. We say they are global. It's a global transformation of the whole image data in every single coefficient. Okay, so that's where we're going to be going later, is to say what can we do to not only handle position, handle intensity, but also to handle it with some notion of level of degree of locality, we call it scale, spatial scale, and region of locality, place that you're interested in. But before that, we are going to talk about choice of alternative basis functions for compression. Okay? So this is the topic of the next part of the course. And what you're going to see is those of you who are not fully sharp, fully educated in linear algebra are going to learn a whole lot more linear algebra in this. Okay? And that's going to be good too because it turns out to be so important for all the things that you want to do going forward using imaging. Okay, so let's start. Let's assume that we have a set of basis images, capital psi, and it's a set of basis images, and each member of the set is orthonormal. That is to say, the sum of the squares of any basis image's pixels is 1. And secondly, the dot product between them, that is to say, the sum of the squares of pixel by pixel, or in 3D voxel by voxel, of one basis image and the other over the pixels is 0, unless you are dot producting one of the basis images with itself. Now, in order to do that, it's just easier to think of images as vectors. So what I'm going to do is, okay, so an image, of course, has rows in 2D. In 3D, you can say it has slices, and the slices have rows. Right? But anyway, what we're going to do is we're going to take this guy and we're going to put it over here. Okay? And then we're going to take the pixels here and we're going to put them here. We're just going to make one big long, if we have an n by n image, we have capital M equals n squared elements in that vector. Of course, this hides the fact that there's particular information about what happens across the rows. But from the linear algebraic point of view, if we're just thinking of linear algebraic operations, we can think of it that way. Later, anytime we call this understanding the image in row major order, and now it's just an ordinary capital M vector, where capital M equals n squared, or in 3D it's n cubed if you have an n by n by n matrix, or n squared times n1 times n2 times n3 if you have different dimensions in each of the x, y, and z. Okay, fine. Once we have one of these, of course, we can go immediately back to here. We take the first so many of the out of this vector and put it here, and the next so many and put it there, and the next so many and put it there, and we can reconstitute the image. So we haven't done any damage to the image information. And from a linear analysis point of view, it's just a little easier to think about these things in terms of these really long vectors rather than an array of images. It just makes us not be confused by the idea that it's a two-dimensional array or a three-dimensional array of pixels. It's just one long vector. Okay, and then we're going to have basis. Our basis images, likewise, are going to be understood in terms of those vectors. And so we will have, if we have exactly m of these orthonormal vectors, we will span the space of all images. We'll be able to exactly write any image, I, as a linear combination of the basis images. Okay? Any questions? And because they're orthonormal, we've already talked about the really important thing that is we call it the dot product rule. If you dot I with any one of the psi i's, because of the orthonormality, all the terms psi I dot I psi j go away, and psi I dot psi I gives you 1, and so that gives you a way for computing the coefficients. The coefficients are simply the dot product of the image with the basis image. Okay? But we're going to be interested in compressed images. And the idea is that we are, instead of having big number, capital M, of images, we just want to have an approximate image that is simply the first capital J of these basis images. Idea is to get away with the smallest J we can. The smallest capital J, okay? So we're going to call that I hat J, I hat super J. It is simply the image where we truncate, we essentially set to 0 all coefficients beyond the capital J. And then we're interested in how much error. This is not going to be perfect because these AIs beyond there weren't actually 0. And then we're interested in how much error we're making in using only capital J rather than all capital M of these guys. And so the remainder is the sum of the squares of the difference, pixel by pixel, or voxel by voxel, of I itself with its approximation I hat J. Right? And the sum of the squares is the dot product of this thing with itself, or written that way, where this is a row vector and this is a column vector. You have I minus ij transpose I minus ij, I hat j. Okay, so happy with that? But this is a distributive operation. So you get I dot I transpose I itself, which is the sum of the squares of the image pixels. You get the sum of the squares of the approximation pixels, and minus twice the dot product between I and ij. That's just, you get ii, you get iij with a minus, you get ij dot I with a minus, but dot product doesn't matter whether you do a dot b or b dot a, right? So we're going to be interested in this formula. Now, what we're trying to do is to have this thing be as small as possible over what all possible choices of basis images. Yes? Well, not overall. Let's have a set of training images, as I intimated earlier. So we have a set of, we have I should use J here. Let's call it capital K, basis of capital K, Parceval. I don't know what I've done here. Sorry. I was right the first time. Okay, so now we have a full set of basis images, but we're only using capital J of them, right? Because that's how our approximation is going to work. We're going to send off the coefficients of those capital J if we want to send something from the internet. But the training set itself has M training images. Okay, so if I want pictures of forests, I'm going to have M pictures of forests. If I want M pictures, if I want to do portraits, we're going to have M portraits. People have worked on that problem a lot. These things end up, you'll see why. It turns out Eigen analysis rears its head again, and they turn out to be eigenfaces. Okay, we'll find out why I'm calling them, why people call them eigenfaces shortly. But in any case, we have this set of training images. I underline K, K equals 1 to up to M. And what I want to do is make this error as small as possible. Well, it's an error in a square sense, right? I mean, this is square, some of square differences. But that we want that square error as small as possible, averaged over all the training images. So I've set up this problem. I want the smallest average error over the training set. When I only use capital J of them. And I'm going to want to solve the problem first for capital J equals 1. What if I only want to use one basis image? Then we'll solve the problem for capital J equals 2. What if I allow myself to have 2 basis images? What should the basis images be? And what we'll end up seeing is that the solution for 2 has the first one, the one we had it for capital J equals 1 as one of the basis images, and we add one more, which is orthonormal to the first one. And then the third one is going to be orthonormal to the first 2, but the first 2 are going to remain the same. Okay. So we got another sum over all the training cases. So we want this error to be as small as possible. Well, the M doesn't matter. If we want to minimize this thing, we can just minimize M times it, and it won't change what the result is. So I'm going to not keep this average idea. It's just going to be the sum of all the square errors. Okay. So that's our problem. And in order to understand how we're going to solve it, we need a very interesting property of all orthonormal sets. And it's called Parceval's theorem. And at most times you'll see Parceval's theorem stated in terms of the orthonormal set of sinusoidal orthonormal basis images. But in fact, this is a property, doesn't depend on the sinusoidal set or anything like that. It's true for every orthonormal basis set. Okay? And the basic notion is if we have a different basis set of orthonormal images, we can write the same image as some bi phi. I equals 1 to the same total number. Right, we haven't done any compression yet. We've taken all capital M basis images. But if we look at I dot I in this representation, and look at I dot I in that representation, the dot product, you get a double sum. Sum I equals 1 to M of AI psi I transpose times some, let's call it L equals 1 to M of AL psi, oops, use superscript here, psi L right, that's just I dot I, written twice. Just to not confuse things, I've let my dummy variable that I'm summing over vary. But the point is, when you take this double sum out, you get terms summed over I and L of AI AL psi I transpose psi L. And all these are 0 if I is not equal to L because of the orthonormality. And when I is equal to L, it's 1. And so this thing turns out to be simply some AI squared I equals 1 to A. Right? The sum of the coefficients squared is some AI squared. And if I play the same game here with different images, I'm going to get I transpose I equals some bi squared. Put another way, once I've done all this, I've used the fact that they're orthonormal, but nowhere in the final result does actual psi I appear. The sum of the coefficients squared is independent of the base of the orthonormal basis set we use. For every basis set, the sum of the squares of the coefficients are the same. So the idea is we can consider this sum of squared to be a budget that we get to spend on a lot of the budget for some of the images and much less of the budget for other of the images. And the question is, which members of the budget produce this least average error over the training set? How should we choose our basis images so that our budget is spent mostly on the images on the basis set that are used first and very little on the basis set, on the elements of the basis images that are later? Okay. Well, in particular, notice that one particular basis set that is orthonormal are the delta images. Yeah, those are the images that have, right, a 1 in one place and 0 everywhere else. Right? Sure, they're sure orthonormal, right? You take one with a 1 in one place and another image with a 1 in a different place, and you multiply them together pixel by pixel and then add them up. The 1 multiplies by a 0 in both places, you end up with 0. So it's orthogonal. And the sum of the squares of the entries are the coefficients, which is just 1. Okay, so sure enough, that's an orthonormal set. But in that orthonormal set, AI is just the image at position I. The coefficient of the delta basis image is just the entry in the ith position of the image. So the sum of the AI squareds, which is our budget, is simply the sum of the squares of the entries in the image. The sum of the pixel values squared. Sum of the squares of the pixel values. Okay, so that is our budget. We know what our budget is. You put in capital I, and you know that your budget is simply the sum of the squares of the entries in the image. And the idea is to get a representation of I that has most of its spending for small for basis images that are sort of up front in the list, and very little of our spending of that budget in what remains after we've cut off after capital J terms. Okay? So now I've set up that problem, and we're going to run through some linear algebra that does that. But just to give you something of a geometric sense of what we're doing, this picture shows a 3 space of little x's. And our training images are all those little x's. If there were an image with only 3 pixels, then the values of the first pixel is on one of the coordinate directions here. The second pixel value is on the second, and the value of the third pixel is there. Okay, but we're going to have we're going to have a million-dimensional space. The first pixel is the first coordinate, the second pixel is the second, the third pixel is the third, the fourth pixel is the value in the fourth, and so on. Okay, so we have and this set of x's is our training images now, shown if we only had 3 dimensions. And the basic idea is that we're going to find out that there is a particular direction in this space, a particular unit vector in this space along some direction, such that the deviation of each of these from its line in a square sense, of this, those distances squared are going to be as small as possible. Right? So we're going to be asking which straight line passes sort of so nicely among the data so that this is going to be the best solution. And when we want two basis images, well, two basis images form a plane, right? One vector is a direction. Two vectors, if they're orthogonal, span a plane. And then we're asking what's the best fitting plane to the images. And we will end up seeing that that plane includes this line and another direction orthogonal to that line. And so that the orthonormal set consisting of those two is going to be the best two basis images. Okay, so we can understand. And then obviously the next piece of the story is going to be we're going to have a three-dimensional flat space that is the best fitting flat space, and you're going to need a third vector orthogonal to the other two to span that three space, and so on. So that's what's going to be going on here in all the algebra that we're doing. Okay, so in this stuff on all this algebra, instead of using psi I call it ui. Right, those are the basis images. Okay? And this Parceval's theorem is what I told you that no matter what set of basis images, you still have the same budget for sum of the squares of the coefficients of any image in that basis. And in particular, that is the sum of the squares of the original image's pixel values. Okay. Well, a good way to think of a basis is as a matrix. We're going to talk about a matrix, capital U, that looks like this. I'm just going to take my basis vectors. Each of them is a capital M tuple, right? So there's M of these, and there are M of these, so it's a square matrix. And its columns are simply the list of the basis images, right? Well, images with the spread out into one big long by this row major rewriting of the image. Everyone understand what capital U is? And then there's a bunch of algebra here that says when I want the coefficient of my basis set, the ith coefficient of the basis representation of training image IK, the whole thing ends up being that it's because the dot product rule is the dot product between the image and the basis thing. And if now I take the tuple of coefficients, B1, B2, B3, and think of it as a vector, B, which is just, right, B1, B2, Dm. It turns out I can write that BK is just the transpose of capital U times the K times that training image. So the representation of a training image has a whole set of coefficients, and it's got by simply for any image I. And so in particular, when I'm writing the kth training image, that's the representation of the kth training image. Okay? Anybody have problems with what's happening here? Okay, and then we're going to define this image represented only up through capital J terms. And what that's going to do is have a set of coefficients that are up to J, the same as here, but then it has all zeros here. Meaning I'm throwing away the information, the coefficients in beyond J, beyond the capital J. Okay? Okay, well, all the nasty looking algebra on this thing comes to the conclusion that you can calculate what the budget is, and it's a fixed budget, and the sum of the squares of the kept coefficients is what push is the budget usage. So if you look at the ratio of some bi squared from I equals 1 to j, and divide it by some I equals 1 to m of bi squared, but this thing is also, we've shown, equal to I equals 1 to m of the image pixels squared. What we're trying to do, what we're going to be arguing, is that maximizing this, spending the most of our budget as a fraction of the total budget on the first j of them will, in fact, minimize. Where did I have it? I guess I've lost it. Yeah, there it is. This guy. We'll minimize that error on the average, over the training image. That's essentially the way the proof goes. Yeah. What's a training image? It's one of those images that we're using as sample. If we do forests, we're going to go get 1,000 images of forests, and each one of them is a training image. If we do portraits, we're going to get 1,000 images of people's faces, right? And those are the training image. They're the images that we're going to use to represent the set of the space of all images of portraits in the case of portraits, or forests in the case of forests. And we're trying to minimize the average error over all of those training images. Is that clear? By the way, for those of you who are interested in deep learning, pretty much all of you probably, it's the same notion of a training set for deep learning, right? We're going to get a neural net that minimizes some so-called loss function, which is just, in this case, this error term. And we were going to run the training images into the net and jigger its all its convolutional coefficients in the neural net so as to produce this minimum. Same notion of training images. Okay, so I will if I multiply this B vector by U, I get U transpose IK, and if the columns of this vector are orthonormal, it turns out that means that its transpose is equal to its inverse. That's true of any matrix of orthonormal columns. If you multiply it by its transpose times itself, or U transpose equals U transpose U, which is the identity, which turns out to be the identity matrix. The matrix with all ones on it, okay? Meaning, if you multiply U transpose times U, it's the same as multiplying U inverse times U, which is to say, the inverse is the matrix when multiplied by the original matrix. The inverse of a matrix is something that when you multiply the inverse times itself gives you the identity. Okay? And so, as a result, every time we see U transpose or U transpose U, it's just the identity matrix. And what that corresponds to in geometric terms is that this U matrix is simply a rotation in the space. You remember I brought Tinker Toys and I said you had one basis. Okay, those are three basis images. And now I'm going to get a different basis. That's just a different rotated basis image. And the operator that does that rotation, turns this into that, is capital U. It's the matrix multiplier that rotates your coordinate system. Okay? Okay? It's basically a rotation of the delta basis. Right? The delta basis has one, it's one in the first position, the next element is one in the second, and so on. And capital U tells us that the one with a 1 in the first place goes into U1. The one that has a 1 in the second place goes into U2. The one that is in the kth place goes into little UK. Okay. So this is a bunch of linear algebra. You need to push through these slides and convince yourself that you follow each step, and if you don't, you come into class and you say, I didn't understand this step on that slide, or if you want, you can come do it in office hours. I'm not going to go through the math, but what we end up with is that we're trying to minimize this error term. This guy here says that what we need to minimize is the sum over all the training images IK of IK, the dot product of IK transpose with U1 times the dot product of U1 with IK. But that, of course, because dot product, the order doesn't matter, we can write this as IK transpose U1 all squared. And we prove that minimizing that error is the same as maximizing the budget, the fraction of the budget that we're using. Okay? But this particular thing is just choosing U1. What is the best one basis image? So that if we cut off everything beyond that, 2 through n, we get the best estimate. It turns out it's that vector, that's that straight line through that I spoke of. And we prove here that that one is the best single basis image to use. We're not going to use any of the others. Okay, then we go on to our problem of choosing 2. And the proof goes on to show that the 2 best ones are the first one, you don't change the first one, and another one that is orthogonal to it. And what it does is you've used as much budget on the first one as possible, and now you have a remaining budget, the total budget minus the budget you've spent, and you're going to maximize over all possible second images the increase in the budget fraction that you use over and above the first one. And that'll give you another orthonormal image. And then to get the third one, you play the same game. You've now used up budget spent on basis direction 1, basis image 1, and basis image 2. And you're now trying to get as best you can, get the very maximum amount of remaining budget spent on the third basis image. Okay? So that's how the whole argument goes. And the linear algebra here proves that. Okay. So let's put this whole linear algebra in computational terms. I'm going to talk about a training matrix, a training array. Let's say it will be a matrix, capital A, that looks like this. There are m rows in this thing, and each one corresponds to a different training image. So what have I called it? I1 transpose is this row vector. Training image 1. I2 transpose is this row. I M transpose is this one. It's simply the list of all the training images, right? Well, I am actually going to talk about a Okay, so I'm going to take the first pixel in each column, and I'm going to take its average. Right? And the second pixel, and take the average of the second pixels. And the third pixel, and take the training of. And so this is what I mean by the average training images. I'll call it A bar. But it's the single image. This is not a. A is probably a bad name for it, except that I'm going to repeat it for every single case. Okay. Okay. So this A bar is simply the average, column average each time, repeated. And I'm going to subtract it from my mean. So all I'm going to do is I'm going to take the first image and subtract off the mean. This image and subtract off the mean. This image, training image, and subtract off the mean. Okay? What's going on here, over here, is the mean is, some center point here that is in the center of the distribution. And instead of centering at zero, we're now going to center our coordinate system at the mean. That's what's going on there. Okay, and what's going to happen is that this best direction is going to pass through this mean. Okay, and so we have this mean corrected training image set. And what we're going to end up showing is that the best psi's, the optimal ones, are the eigenvectors of I need a name for this. Let me call it B. Of B transpose B. Whole thing turns into an eigensolution. I'm going to prove that next time. Okay, be careful. A is big, right? It's capital M wide by little m. Okay, so if you have 1,000 by 1,000 images and you have 500 training images, this array has 500 million entries. Yeah.
So each training image itself has its own set of basis images?
Nope. No, there's going to be one. The idea is to get an error that's minimized, averaged over the whole set, averaged over the set of training images. So there's one set that's best for the set of training images, not for an individual one of the training images.
Our training image is an image on itself, though, right? It's
Yes, that's right. You're going to have some error for the first training image if you only use capital J bases. You're going to have some error in training image 2, which is different. You're going to have a different error image. It's an image of pixel errors in training image 3. Right? Yes, there are different error images for each one, and this thing is not optimized to make any given one of them be best, have smallest error. It's that the average square error over all these training images should be as small as possible. That do it for you? So some of them will be larger, some will be smaller, but the average square error is as small as possible. Okay, so we're going to be worried about solving, first of all, proving that this is the case. And then secondly, figuring how to not have to really find eigenvectors of a matrix with 100 million, or whatever I said, 500 million entries. Right? Don't want to have to solve that problem. too big of a problem computationally to solve. We'll find a better way to solve it. Okay? That's where we're going next time.